In this video, I will discuss the use of ARIO in determining the direction of an acid and base reaction. So again, in an acid and base reaction, electrons are being transferred between the base and the conjugate base. So that where electrons start out on the base and it end up on the conjugate base. And therefore, the stability of the base and the conjugate base can dictate reaction equilibrium. And again, here is an overview of the acid and base reaction. So the electrons start here on the base. And the electron end up here on the conjugate base. And the remaining of the acid, that will then be the conjugate base. And the electron end up right here. If there is a reaction. And therefore, to determine how reaction equilibrium will be favored, we have to compare the stability of the base and the conjugate base. If the base is more stable, so if this is more stable, then the reaction will favor the reactant side. So reaction favors reactant side. And therefore, there will be no reaction. Because if electron is stable on the reactant, or stable the way it is, then there will be no need for it to undergo any chemical changes, because the electron will then be in its most stable state already. But now, if the electron, this base right here, is not as stable, where it will be more stable here on the conjugate base side, then there will be a chemical reaction. So if the conjugate base has better electron stability, so if this is more stable, then the product side will be favored. And therefore, there will be a reaction. So knowing how to compare the electron stability between the base and a conjugate base will then allow us to determine reaction equilibrium. And again, ARIO stands for atoms, resonance, induction, and orbital. So these are the four effects or the four factors that allow us to qualitatively compare the electron stability between the base and the conjugate base. For an example, predict the products of the following reaction and use ARIO to exist in your prediction. So here an example right here, and so this is an acid and base reaction right here, and the reason why of why this would undergo the acid and base reaction is because of the following. And again, let's now first analyze the electron stability and the electron distribution in both this molecule. So we can see oxygen has a negative charge on it. So this tells us this oxygen right here is very rich in electron. And although we're not drawing this out, but you need to recognize that this oxygen right here has 3 lone pair of electrons on it. And this is electron rich. So that's what's happening with this reactant. Now on the product side, if we were to analyze the electron density, this oxygen right here is partially negative, and this hydrogen right here is partially positive. And so we can see this hydrogen right here is partially positive. And this is the distribution of electrons in this molecule. And because this hydrogen right here is partially positive, it will then be attracted to the lone pair of electron on this oxygen right here that is negative. And therefore, electron from this oxygen will then be donated to this hydrogen. And as we draw this arrow, we basically saying that this oxygen is donating electron to this hydrogen right here to form a bond. And that caused this hydrogen right here to exceed its bonding limit because it can only make one bond. So therefore, it has to donate the electron that is involved in this bond right here to the other oxygen. And now on the product side, we'll have the following: CH3, CO, and now this oxygen right here would end up with a lone pair of electrons. And this makes this oxygen become a negative because before it was neutral. When it gained the electron from this bond, this oxygen right here getting 1 electron, so it will then go from neutral to now negative. And as for this hydrogen right here will now end up with the hydroxide, and that make up water. And this oxygen would now be neutral, because when it happened this way, this oxygen is given an electron to this hydrogen. So that's why it will go from negative to now neutral. And that is what we would have. So if a reaction is going to take place, this would be the products that get produced right here. And we can see that the electrons start out here. And in fact, this is the base. So electrons start here. And this is the base. And this is the acid. And as for this acetate right here, this will then be the conjugate base. And this water, this will then be the conjugate acid. And make sure you know how to classify and determine the acid, the base, the conjugate acid, and the conjugate base. So when we use ARIO, we need to compare the stability of the base, because that's where electron is starting from, and the conjugate base, because in the end, that's where the electron end up with. So this base right here give the electron to this proton, and this proton then give the electron to the rest of this molecule. So the rest of this molecule then become the conjugate base, and that's where the electron end up with. So therefore, to determine the directions and the equilibrium of this reaction, we need to compare the stability of the base, which is the hydroxide, and the conjugate base, which is acetate. And here in this case right here, we can then see that acetate is more stable. And this is more stable because of resonance. An oxygen, an acetate, is able to form resonance with the other, to donate electron to the other oxygen, and therefore allow the electron to be distributed between these two oxygen, and that reduce the buildup of electron density on this molecule and make it more stable. And so this is how we can use ARIO to help us in figuring out the direction of acid and base reaction in this example. Now let's now try the reaction B. So here is what we will have right here. And again, first analyze the electron distribution on the two molecules. And again, pay attention to the most electron rich and the most electron poor atom in this molecule. So here in this case right here, we can see this oxygen here is positive. So this entire molecule right here, it basically is electron deficient, right? And so this is electron deficient, making it positive. And here in this case right here on the other molecule, we can then see that this oxygen right here is rich in electron, because they have two lone pair of electron on this oxygen. So this is rich in electron, and this entire molecule is deficient in electron. Now, particularly, here's what happened. One of this hydrogen right here is very, very partially positive, because when this oxygen right here, it has a positive formal charge on it, it basically will attract all of the bond pair electrons in this three bond that it has to this oxygen, making this hydrogen right here become very, very partially positive. But only one of them will participate in chemical reaction. So in the course of this reaction right here, the electron from the lone pair electron on this acetone will be attracted to the partially positive charged hydrogen and forming a bond between this oxygen and this hydrogen, causing this hydrogen here to again exceed its bonding limit. So therefore, it has to break this bond, one of this bond, and now the electron is then donated to the oxygen. So on the product, this is what we would have. So the oxygen now will be bonded to the hydrogen, and this will then cause this high oxygen here to have a positive formal charge on it. And when this electron is donated to this oxygen would now have two lone pair of electrons, and it would then be neutral. So that will be the product right there. And now we have to identify the base and the conjugate base. So here in this reaction right here, this is the base, and this is the acid, and this will then be the conjugate acid. So Ca stands for conjugate acid, and this will then be the conjugate base. So we have to compare the electron stability on the base and the conjugate base. So between these two molecules right here, which one will be more stable? And here in this case right here, we see the following. So the lone pair electron on this oxygen right here, on the reactant side in acetone, this electron right here locate on an sp2 orbital, versus the electron now end up on this oxygen, and this oxygen right here in water, the lone pair electron right here locate on an sp3 orbital. So the differences between these two substances is that one of them have electron locate on an sp2 orbital, and the other one have electron on an sp3 orbital. And here in this case right here, we will then see that the electron on an sp2 orbital is more stable than electron on the sp3 orbital, because the electron on the sp2 orbital are basically much closer to the nucleus compared to sp3, and therefore are more stabilized. So basically, the electron is stable on the reactant side. So the reactant side is more stable than the product side. So here in this case right here, we will think that equilibrium will then favor the reactant side. So this means no reaction, because there's no need for it to transfer the electron and put it here on this sp3 oxygen, whereas it already more stable on the reactant side the way it is. So in this case, there will be no reaction.